Hi everyone, this is your week 10 video on half-life and nuclear energy. This corresponds to unit 6C and 6D in your book. Today we're going to look at what is half-life. We're going to define it and describe it. When you're going to be able to calculate the amount of a particular radioisotope that remains after half-life. The key here is it's half. So every time a certain amount of time goes by, half the sample goes away. So it's going to be really easy. You're just going to be dividing by 2. We're going to look at radioisotopes and their uses. We did a little bit of that last week. We're going to define and describe nuclear fission and nuclear fusion. We're going to describe how electricity is generated in a nuclear power plant. And we're going to end with types of nuclear waste and their sources and disposal methods. So first, how fast do radioisotopes decay? Well, it's different for every element. A half-life is the rate at which the isotope decays, and it's measured in half-life. So the term half-life is defined as the amount of time it takes for half of the sample to decay. Half-lives will be, for various radioisotopes, can range from a few microseconds to billions of years. So for the dangerous radioisotopes, it's going to be, they decay really quickly and they emit strong radiation so that you're getting this constant release of powerful radiation. Whereas the more safe radioisotopes are going to be the ones that their half-lives take billions of years to decay. Unfortunately, if they're dangerous to have around, then that's not a good thing because it takes forever for them to stabilize. A decay curve for radioisotope is listed here. You're going to see this in part C. You're going to plot the points for a graph like this. Notice that if the sample starts at 100, so it's in percentages. So say you have 100% of your isotope to start with. After a set amount of time, you have 50% left. Half of the sample has decayed and one half-life has occurred. Once another half of that remaining sample decays, so half of 50 is 25, now you're at 2 half-lives and you're left with 25%. When that sample decays, half of that is 12.5%. So after 3 half-lives, you have 12.5% remaining. And you can see the picture here. You have what's happening is the radioisotope is decaying and its nucleus is emitting energy and or a particle, and then you have its daughter nucleus that is produced, if you want to call it that. So you've got the original, this is the parent isotope, and then you have some parent isotope left, and you have half of the sample is daughter isotopes. Then you have a little less parent isotopes and more daughter isotopes, and then you have even less and even more of the daughter isotopes. So it's decaying, and you can see that it goes down pretty rapidly at first. So examples of this, you can have hydrogen-3, which has a half-life of 12.32 years. So every 12.32 years, half of the sample will decay and emit particles or energy from the nucleus. This is a mild radiation. It's used in commercial, military, and scientific endeavors. It's relatively safe. It doesn't penetrate human skin. And then you have carbon-14. Its half-life is 5,730 years. So every 5,730 years, half of the sample decay, and that's going to be when it emits either the particles or the energy. We use this for radiocarbon dating. So when you hear about carbon-14 dating or carbon dating, this is the isotope that they're measuring the half-life of to figure out how old the sample is. When we calculate this, you're essentially just dividing by 2 every time. But first, you have to figure out how many times do I have to divide by 2? How many half-lives occur? So in the example provided, it says iodine-131 is a radioactive isotope and is often used in certain medical treatments. It has a short half-life of about 8 days. If a hospital has a 100 milligram sample of it available, how much would it be available after 24 days? So the first thing you have to do is figure out how many half-lives occur. How many times you're going to have to divide by 2. So you're looking at the total amount of time is 24 days. If we divide that into 8-day sections, each section of 8 days is 1 half-life. So if we take 24 days divided by 8 days, we can see that there's 3 sections of 8 days or 3 half-lives. So we're going to divide by 2 3 times. So the second thing is now we're going to divide by 2. We're going to take that initial sample size of 100 and we're going to divide it by 2 and get 50. So after the first half-life, there's 50 milligrams remaining. We divide by 2 again, and after the second half-life, there's 25 milligrams remaining. Then the third time, so now we are at 8 days for the first half-life, 16 days for the second half-life. Now we're at 24 days. We divide that 25 milligrams by 2, and after that third half-life, we end up with 12.5 milligrams. So the question is asking how much is available after 3 half-lives, or 24 days, so there'd be 12.5 milligrams left. And that allows doctors to determine the dosage and the frequency of medication and treatment when working with an isotope like this. And there's a nice pie chart or circle graph visual of this to the right. So you have your initial amount is 100%. After 1 half-life, it's 50%. You take half of it's gone. Divide by 2 again, 25% remain. And then after the third life, about 12 or 12.5% remain. So how do we use radiation? We talked about this a little last week. We can use it to analyze matter as a tracer, to diagnose medical problems, and to treat diseases. This is a repeat slide from last week, so this is a review. So when we analyze matter, we can use it in museums or crime labs to look at art forgery or gunpowder residues. Tracers are going to show the effects of the herbicides and the pesticides and fertilizers by attaching a tracer to those things. You can see where throughout the plant it goes. Diagnosing medical problems, we have iodine-131, technetium-99M, and phosphorus-32 used to detect different medical problems. And we can treat diseases with radiation. We can treat cancer, and we can treat thyroid disease. So we're going to talk about 2 different types of nuclear decay today. We're going to talk about nuclear fission, and we're going to talk about nuclear fusion. So when we talk about nuclear fission, we're talking about the splitting of an atom. So the atom is bombarded by the nucleus by neutrons. So you take a neutron and it is bombarded or shot at the nucleus of an isotope. And what's happening is it's going to create a reaction. And like this here, we have a neutron being bombarded into the uranium isotope. And it's going to create a very unstable uranium isotope, which is then going to release energy. It's going to release a krypton nucleus, a barium nucleus, and 3 neutrons. What happens is then those 3 neutrons go and strike other unstable isotopes or stable isotopes that's fissionable and create more reactions. And we end up with this chain reaction. So the neutron strikes one nucleus. That nucleus, when it splits, also gives off neutrons from fission. Those then strike other nuclei, and then it continues, and it gets really big really fast. So it's important to control the reaction. When we use nuclear fission, we have different methods to control it so that we can produce energy without producing too much energy, so it's unsafe. An example is the fission of uranium-235, which is right here. So that chain reaction is that more neutrons get released and they strike nuclei of other isotopes. So what happens is these are usually really large and not as stable types of reactions. Nuclear power stations will use the heat released by nuclear reactions or nuclear fission to boil water to make steam. And you're going to read a little bit about that during part B. The other example is nuclear fusion. So if nuclear fission was the splitting apart of nuclei, nuclear fusion is the combining or the making of a bigger nucleus. So fusion occurs when 2 small nuclei combine to create a nucleus that has more mass. This will also release energy. It actually releases more energy than fission. And this occurs at very high temperatures. So it occurs on the sun and in the stars, because the sun is a star. The hydrogen bomb is an uncontrolled fusion device. And this occurs naturally in the sun and the stars. So you can see kind of a picture to show this at the bottom. You've got a few nuclei here. You've got 4 hydrogen nuclei, and they combine to form a helium nucleus and 2 electrons that get emitted. 2 positrons that get emitted, and then also energy. So that energy release is quite large and larger than fission. Nuclear power, currently there's 103 nuclear power plants in the US. There's currently about 435 worldwide. 17% of the world's energy comes from nuclear. This kind of shows the breakdown between different countries. So we're ranked 19th. We get 19.9% of our total power from nuclear, but you can see at the top, France and Lithuania are using that as their main power source. And what happens is you have these things called control rods, and you can move them up and down to make the reaction go a little faster, a little slower, and they're in the same space as the fuel rods. And then the energy is then heats up the water, creates steam, and the steam turns the turbine, which creates the electricity through that mechanical transfer, mechanical energy. A nuclear power plant can have nuclear explosions. An explosion occurs when the reaction is allowed to run out of control. This would be when large amounts of energy are released very quickly. Some of the things I said before, you've got the nuclear reactor, it can control the rate of energy release. The uranium oxide is in the fuel rods, and the rods are lowered into the reactor core. There's a coolant used. In most of them, it's water. In Millstone, it's water. It's circulated to remove some of that heat. The control rods can absorb those extra neutrons from that chain reaction, and it can lower the rate so it doesn't cause an explosion. And then that control rods can be raised up and lowered to kind of feed into the purpose that you need for it. If there's a nuclear explosion, it's not radiation that's being exploding. It would be a release of heat and light. It wouldn't be nuclear waste that gets kind of exploded from the power plant. So that's kind of an important distinction. And then nuclear waste. There's two types of waste. There's high-level waste and low-level waste. High-level waste are like the products from the nuclear fission. So that's the products directly from the reactors. These are the transuranics, the products that when original U-235, uranium-235 fuel absorbs neutrons, so that's direct fuel. So the disposal of this is stored on site of the nuclear power plants in the limited capacity and storage tanks, and then it'll get moved to a permanent repository available, and then the federal government will be responsible for that final storage. The low-level waste is like the protective clothing and the diagnostic radioisotopes and the air filters from the power plants. Those all have a low-level waste. Those are in a sealed container and can be buried 20 feet deep in lined trenches. And then waste volume versus radioactivity level. A high volume does not necessarily mean high radioactivity. You could have a lot of low-level waste that doesn't have a high level of radioactivity, and you can have a small volume that is very radioactive. So there's a little bit difference between your waste volume, how much of it you have, versus the radioactivity level. So let's review. So we have a half-life. It's the amount of time for a half of a radioisotope decay, and it's going to be different for every single substance. Every substance has its unique half-life. We use radioisotopes to analyze matter as a tracer in diagnosis and treatment in medicine. Nuclear fission is the split apart of a nuclei. Nuclear fusion is the combining of nuclei. Both will release enormous amounts of energy. Fusion will release more. Nuclear power plants use nuclear fission, and we use control rods to control how much energy is gained from those reactions. We have low-level waste like your protective clothing, air filters, diagnostic radioisotopes. They can be sealed in containers and put in 20-foot lined trenches. We have high-level waste, products from nuclear reactors and the transuranics. These are disposed in nuclear storage tanks and then handled by the federal government for its final storage. So I hope that this helped for you. Again, in part B, you're going to be reading a little bit more about nuclear power specifically. So I gave you kind of the nuts and bolts. You'll learn more in part B. And part C, you're going to be exploring half-life and what the graph looks like and kind of determining the half-life of a sample. So you're going to do great. If you have questions, reach out. You know when my office hours are, and I'm available through email at all times. All right. Have a great week, everyone, and good luck.